Hello and welcome back to yet another lecture on the advanced plasticity of solid continua, the NPTEL course. In this lecture, obviously it is a continuation of the last lecture. So, in the last lecture we were talking about the various types of rate dependent plasticity, including those which do not need the notion of an yield surface, and the Perzyna type model which requires the notion of an yield surface, right. So, we discussed that. We knew how to determine the plastic the potential, that is the phi, that is the dissipation potential for the Perzyna type model. And we said that thanks to this kind of the availability of the dissipation potential, which is a convex function, strictly convex function, we can make use of this to derive a variational principle to determine the unknowns in a finite element framework, right, just as we do in elasticity. This is the greatness of, actually this is the great aspect of using convex analysis, right, in understanding plasticity. So, in this lecture we will be discussing the variational treatment, the variational framework set up to solve for these unknowns, right. We will start. So, the variational framework consists of two problems. So, one is a local problem, which is to find the plastic flow rate or the hardening variables, combination of them, all the internal variables, right, call them alpha. Alpha are the internal variables, right. Now, alpha can just consist of epsilon p dot, okay, in many cases, because if you recall that many of the hardening variables, including the kinematic hardening as well as isotropic hardening, these are also expressed in terms of epsilon p dot, right. So, the plastic strain rate could be enough to determine all these different parts of alpha, right. Now, determining this alpha or epsilon p dot is the first problem. It is a local problem in the sense that you do it at every material point. In a finite element setup, you do it at every Gauss point, that is every point where you do integration, right. So, that at the Gauss point if you update, then you can actually use that information to do integration later on to arrive at global quantities, right. So, that is why you can do it at every Gauss point. Because you do it at every point, that is why it is called a local problem, all right. Now, let us say we want to determine the plastic strain rate epsilon p dot, okay. So, first thing to remember is that the free energy psi can be written as a function of only epsilon E, but epsilon E is the elastic part of the strain. Now, epsilon E is nothing but epsilon minus epsilon p, total strain minus plastic strain. So, that actually is available, let us say, with us, because the elastic properties of the structure should be known. Now, for a given stress, or more generally the thermodynamic force X, okay, for a given stress sigma, let us say, we can solve the following optimization problem. This is a local problem to determine epsilon p dot, the plastic strain rate. Find, so let us consider this as the functional to be minimized, right. So, call this functional by Jv equals phi of v. V is a velocity like object, actually the plastic strain rate like object, right, minus x dot v. A dot means an appropriate inner product. For example, if it is the a product of stress, x in the form of stress and v in the form of epsilon p dot, then this dot has to be replaced by a colon, that is the Frobenius inner product, right, you should recall that. So, it is an appropriate inner product. So, your job now is to find epsilon p dot by minimizing this Jv, this quantity, with respect to v. Find that v for which this is a minimum. Why is it so? Why do I claim that this is the correct v? this is the correct J, correct functional. The reason for this is that if you actually do the minimization, that means differentiate J with respect to V and set it to 0. Because we are using the language of subdifferential, so that is why we are using a bit of a more mathematically refined language. That is why I wrote it as 0 belonging to del V of J. This essentially means that 0 equals gradient of J with respect to V, right. That is the requirement in this case, because of the simple fact that everything is smooth. So from here what do we get? You just differentiate this JV with respect to V. So we get x equals the gradient of phi with respect to V. This is nothing but the gradient with respect to V of phi. You see that, okay. So basically what we have here is that x in this case is a gradient, a potential like follows directly from the potential stress. So the local minimum, since x is del phi V is basically the known flow rate, flow rule. So therefore this local minimization must make sense, right. You observe that, because we know that this is the correct representation of stress from the flow rule, right. You remember the flow rule is sigma is basically in del phi, right. Similarly epsilon p dot belongs to del of phi star. This phi is a function of epsilon p dot, and this phi star is a function of sigma. You remember these things, right. We have been discussing this for quite some time now. Okay, so because of this treating J to be the objective functional for this local problem makes sense. So you now know how to solve for, in principle, without getting into the details of how to actually put it in a computer. You know the principle behind the determination of epsilon p dot, right. Now we come to the next part of it, which is the global problem. To find epsilon p dot, we assumed that all the other quantities are known. What are the quantities known? For example, the strain is known, epsilon should be known, right. Otherwise it is a problem, right. But that actually has to be found. So because determining epsilon p dot changes epsilon, right. So the global problem will now try to set the epsilon right, the strain it has to find now, right. So the global problem is the entire boundary value problem over the material domain omega, right. So the alpha is the internal set of internal variables, as we have been saying, plastic strain rate plus the hardening variables. The Helmholtz free energy is a function of epsilon and alpha, right, and the dissipation potential is a function of alpha dot only, okay, because alpha dot is, you can think of alpha dot to be equal to epsilon p dot in most cases. So the incremental functional, why incremental? Because here everything is in terms of the derivatives, right. We have it is basically we have psi dot here, phi of alpha dot, right. So basically if you want to discretize it, then because it is in terms of the derivatives, you have to do it over time differences, short time differences, right. Let us say t from t at tn to tn plus 1, 2 time instants close by, okay. So that difference, over that difference. So this functional, the energy like functional, now it is a global problem. So it is, there is an integral over omega, is this, it is the integral of psi dot plus phi of alpha dot integrated over omega with respect to the volume minus the external power input. So external power input, that expression right, it is simply given by external power is integral b dot u dot is the material velocity over volume, okay, plus over the Neumann part of the boundary if traction is specified. You know, the entire body, you remember, right, is split into two parts. One is the Neumann part. So, this is the body omega, this is my del omega, right, the boundary, correct. The boundary has two parts. This part, let us say, is the Neumann part, del omega n, right. The other part from here to here is the Dirichlet part. It is, let us say, del omega Dirichlet d, correct. So, that the union of del omega d plus del omega and del omega n gives you del omega, right. There should be no boundary, no part of the boundary left without the specification of a boundary condition. It does not make sense. Okay. So, del omega n is the Neumann part of the boundary. This T is the traction vector, right, traction specified over the Neumann part of the boundary. That means the external load. On the Neumann boundary, you have to apply an external load appropriately, right. That is my T, this T. Okay. So, these are the different, you know, that is also multiplied by this T also is multiplied by u dot. So, this is the external power expression. Okay. So, we need to actually, so because this is an energy functional, this pi is an energy type functional, we have to minimize it, right, to find my unknowns, right. So, you know, this is basically an expatiation over whatever we have discussed so far. U dot is the material velocity, right, del omega n is the Neumann part of the boundary of del omega, same thing. B is the generalized body force. So, by the way, if you have forgotten, I should, you know, refresh your memory that generalized body force is a combination of the actual body force, let us say B0, minus the mass density times acceleration, right. You recall that when we discussed briefly the introduction to continuum mechanics in the first 2-3 lectures, then we did, you know, define this generalized body force. Okay. T is the traction vector. By the way, n is the unit outward normal to the Neumann boundary, okay, that you know, and Pext is the rate at which the environment is expending power on the material body. Okay. Now, let us come to the solution. To do that, first observe that at a material point we have the first law of thermodynamics. It is given by sigma epsilon dot equals sigma inner product epsilon dot, okay, that is the total power. Part of that is the elastic power psi dot and the rest of it is dissipation d. What is d now? We have a, because thanks to the convex analysis, we have a very easy way of identifying d with phi of alpha dot. That is, the dissipation potential itself is this d, right. That is exactly what actually came here, if you remember, you know, this is my stuff, sigma inner product epsilon dot, right. That is exactly here too, psi dot plus d here too, that is equal to sigma inner product epsilon dot. So, now so that is the first law in the local form. The integral form of the first law of thermodynamics is just the integral of this local thing over the domain omega, right. So, just integrate over omega, which is written here. Now comes the important thing, which is the principle of virtual work. You may have already been exposed in some other course in your undergrad days or sometime in your postgrad days also possibly, to the principle of virtual work, but I will try to explain to you the essence of it, at least in this present context, all right. So, let us assume that delta u dot is the material velocity, but let us assume that delta u dot is a variation of that material velocity which already solves your problem. Out of all possible u dot, there will be one which will be actually the corresponding to the solution of the problem, right, that u dot we are talking of. So, delta u dot is a variation about that, please remember that. Moreover, this variation must be feasible or admissible. That means if you are solving a smooth problem, you can't have delta u dot defined by a non-smooth function. That is not right, because it will not satisfy the corresponding differential equations which govern the original problem, right. Moreover, delta u dot must be consistent with the boundary conditions. Specifically at the Dirichlet part of the boundary, delta u dot must vanish, because over the Dirichlet boundary we know the solution already, because on the Dirichlet boundary we specify the displacement or deformation, right. So, these requirements together constitute the admissibility. Delta u dot must therefore be admissible in this sense. Similarly, let delta alpha dot be any admissible or kinematically feasible incremental velocity of the internal variable. So, this variation is also on that alpha dot which solves the problem, right. This is a very important point. Otherwise, if you have not solved the problem, I mean suppose you do not know the actual solution, which you do not know anyway, but if you assume that u dot and alpha dot is any other solution which does not satisfy the governing equations, then this principle of virtual work, taking variations of them and invoking this principle of virtual work will be wrong. Please remember that, okay. So, these variations are all about the true solution, okay. The principle of virtual work, we use the acronym PVP for this. So, the PVP then states that given this true sigma, epsilon and alpha, right, sigma is the stress, the virtual delta epsilon and delta u dot, delta epsilon dot sorry, and delta u dot and delta alpha dot, remember that these two are related, right, okay. So, you can actually differentiate delta u dot with respect to x and get delta epsilon dot. Appropriately you have to differentiate, you have to take the symmetric gradient. Okay, so these virtual velocity like objects must continue to satisfy the global power balance. That is a very strong statement. That means you are already in, you have already solved the problem, you are in a form of mechanical, it is not exactly equilibrium, because plasticity, mechanical equilibrium, yes, plasticity still corresponds to mechanical equilibrium, but not thermodynamic equilibrium. So, let us not complicate our stuff, okay. So, forget about the thermodynamics. So, say that you are already in mechanical equilibrium, your sigma, epsilon and alpha correspond to mechanical equilibrium. Take the variation about these, about those values of sigma, epsilon and alpha, and then write your first law, the balance in terms of those variations, it will still hold. That is the principle of virtual work, okay. So, that would in other words mean that since if you take the difference between this left hand side and right hand side here, then this is nothing but the variation of the total power, internal minus external, right, or external minus internal, variation of that, virtual variation of that power. What principle of virtual work states is that the variation of that power will also be 0. You understand? Okay, so pi as a function written in terms of these virtual velocities will be simply the integral over omega, virtual variation of psi dot and virtual variation of phi, but virtual variation of phi is nothing but phi of the virtual variation, right. So, minus the external power computed in terms of these virtual velocities, okay. Now, first let us deal with this term delta psi dot, okay, virtual variation of psi dot, that is equal to del psi by del epsilon, virtual variation of epsilon dot plus del psi by del alpha, virtual variation of alpha dot. This you remember, okay. This is hopefully clear to you, right. Now, you have to come to this term. This term is a tricky term, right. So, you see something like, for example, let us say that phi is equal to some epsilon p dot square, something like that. Then what is the variation of phi? This virtual variation of phi is simply something like half of epsilon p dot, okay, delta epsilon p dot, something like that. No, you understand. So this is what we will be using now in the next slide. Okay. For the time being, let us see this. We will come to the details of these variations further. Variation of phi also we will come to, but in the meanwhile note that delta epsilon dot we need. So that is the virtual that is the symmetric gradient of the virtual material velocity, correct, which is this symmetric. Okay. So, but it is multiplied in the power, in the expression for power, this is this virtual velocity delta epsilon dot is multiplied by sigma, which is symmetric. So therefore only the symmetric part of this will be of interest, right. So in other words, I can say that even if we put the anti-symmetric part of this delta epsilon dot into it, then that multiplication or inner product with sigma will go to 0, right. So it is as good as writing this as sigma inner product, the gradient, full gradient, not just the symmetric part, right, of delta u dot, thanks to the symmetry of sigma. Now the PVP implies that delta pi is equal to 0, right, that we have already seen, that I have already explained to you. Delta pi equal to 0, in other words, we will have to take the variation with respect to u dot first, keeping alpha dot fixed, and then get this delta u dot of pi equal to 0, and then keep u or u dot fixed, and then vary alpha dot, virtually vary I mean, and get delta alpha dot pi equal to 0. Okay, so let us expand these variations one by one systematically and see. Alright, so first consider delta u dot of pi equal to 0, where we hold delta alpha dot equal to 0, okay, only vary u dot by virtual means. So this gives this obvious thing, this is a pretty well known, this is a pretty simple thing to see. I am not explaining this, you should obviously see that we hold everything fixed except delta u dot, correspondingly delta epsilon dot changes, and here is delta u dot, delta u dot. Note that this T, this B, this sigma are held fixed. Why is it held fixed? Because these correspond to the equilibrium, mechanical equilibrium, for which u dot is fixed, epsilon dot is fixed, epsilon is fixed, right, and so on, right. So now since sigma is symmetric, we can write it this way, okay. So this part is written here, alright, and then the rest of it is the same. Now you see there is a very interesting structure here. There is a gradient term in delta u dot. What I want to do is to take that gradient term on that other part here. I want to take that gradient term on sigma, you see. So to do that, what is the method? Integration by parts. So what is the integration by parts? Use this simple formula, okay. So and use that here, right, use that in the first term, volume, in the volume integral. So what do we get? We get basically one term which is the pure divergence here, okay, the other term which is the divergence of sigma term, and as I said that variation, so sorry, the gradient is freed from delta u dot. So delta u dot comes out in both the cases, and then this part, of course, you see it is a pure divergence term, this part. So if you integrate a pure derivative, then you get the boundary term, right. This is something that is in elementary calculus. So the first term is a pure divergence term, so apply the divergence theorem, if you are not very confident, then this gives simply this term, right, over the boundary. Which part of the boundary? Only over the Neumann part of the boundary, because on the Dirichlet part everything is known, the deformation is known, and then rest of the terms you just write. Now organize these terms. How do you organize this term? You put the boundary terms together and put the volume integrals together, and then take out delta u dot, because it is a virtual arbitrary variation. Other than admissibility, there are no further demands on delta u dot. It is arbitrary. So, take it out as a factor and see what is coming within the brackets, bracket within, okay, for which delta u dot is a factor. This is exactly what is done here. Okay, since delta u dot is arbitrary, and for any arbitrary delta u dot, this quantity has to be satisfied, and since this is a boundary term, this is a volume term, so they have to be separately set to be equal to, they have to be separately set to be 0, and the one way in which you can satisfy all of this is by requiring that the integrand itself is 0. This is 0 and this is 0. What does it mean? We basically come to a very obvious thing that we know. The first one gives you the divergence of sigma equal to B. This equation is known to you. This is the Cauchy's equation for the local form of the linear momentum balance. From the boundary term you get the traction given by sigma dot n. This is the famous Cauchy's hypothesis relating traction and stress that we have discussed in the first 2-3 lectures, correct? So, therefore, we have recovered by holding the delta alpha dot as 0, by holding the plastic strain rate as fixed, we have recovered the basic force balance for the whole body, right. So, now let us work with the other part, that is hold the delta u dot to be equal to 0 and vary only alpha dot, okay. So, hold u dot to be equal to 0, u dot to be equal to fixed, that is delta u dot to be equal to 0, and vary alpha dot, okay, allow delta alpha dot to be not equal to 0. If you do that, now here comes this, so delta alpha dot of pi is del psi by del alpha delta alpha dot here, okay, but this term has to be done with a lot of care, which I have already told you. Delta phi dot, because it is directly a function of alpha dot, so therefore it is of an algebraic type, right. So, therefore, this is just del phi by del alpha dot with an appropriate inner product of delta alpha dot, okay. Recall this, because we just wrote this some time back, yeah, recall this kind of a structure here, okay. This structure you must recall, okay. So, doing this we have got yeah, so this is the thing. So, now as in the last case, we will now take delta alpha dot common outside and see that what comes inside, okay, what comes as a factor, right. So, factorize, take delta alpha dot out and use the arbitrariness of delta alpha dot to localize, okay, just localize this. So, delta alpha dot has gone out. So, you basically now have this requirement, that is q, which is basically the gradient of phi with respect to alpha dot, must be equal to, you forget about this, because everything is continuous. So, this is replaced by equal to, okay. There is no discontinuity or non-smoothness anywhere, right. What we have is that this is nothing but the gradient with respect to alpha dot of phi as a function of alpha dot, you understand. So, that is nothing but equal to minus del psi by del q, call that as del alpha. So, call that as q, okay. This is the Biot equation of evolution. This is essentially what you have by the flow rule. This is basically the flow rule. So, essentially what you have done is that by using the principle of virtual work in a systematic manner, you remember that this is the flow rule, because q is basically a stress like quantity, right. So, sigma is basically grad alpha dot phi of alpha dot, which is equal to grad epsilon p dot, phi of epsilon p dot. Okay, that's the flow rule, right? So this is basically the Biot equation in a more general framework. It is basically the flow rule. So by using the framework of principle of virtual work, we have extracted not just the balance of forces, but also the balance of the internal forces, that way, which actually comes up because of plasticity, that is the flow rule, right. So essentially this therefore offers a unified minimization principle, just like elasticity, except that you are now solving for both alpha as well as u, the displacement as well as the plastic, the internal variables alpha, right. Now we come to the actual implementation, which we will be have to discuss. We will just give a short introduction to this and then stop it. We will actually discuss it in the next class. So what we will do in the time discrete implementation is that we discretize the time axis. So suppose that at Tn we know everything, at Tn plus 1, the next time instant, we need to determine our unknowns. Let us say the time step size is delta t. Assume that all the state variables like un, epsilon n, alpha n are known at Tn, and then to determine the rates, that is the time rates u dot, use the finite difference, so that you write this in terms of un plus 1, alpha n plus 1, these are basically unknowns, these are knowns, right, these are already known. At Tn you assume that everything is known. So this will result in a fully implicit approximation scheme of the backward Euler type, which we will be discussing in the next class. But you also observe at the same time that if we do this, if we exactly do this discretization, that is in time by a standard finite difference, then we can write this pi, which was earlier written in a continuous manner, in terms of this delta pi, the increment over this delta t, the time step, to be equal to psi minus psi evaluated at Tn, that is as a function of epsilon n plus 1 and alpha n plus 1, minus psi evaluated at the last time, right, last available time, which is Tn, plus delta t times phi. Remember that phi is basically an entropy like object, dissipation. So therefore this multiplication by delta t makes sense, right. So basically then otherwise there is no uniformity in the in the units, okay. So minus delta p external. So in FEM this minimization will also be performed using a two level structure, nested structure, that we have already discussed, the local as well as the global form, right. We have already seen that. So the local is about at every material point update of alpha, and level 2 at the structural level or the global equilibrium level. So we will discuss this in detail, and then from there we will see how in the context of finite element implementation, how basically the notion of a consistent tangent comes in. Why is consistent tangent important? Because this consistent tangent determines the Hessian structure, Hessian, that is the curvature like object, which in turn can be used within a Newton-Raphson like scheme to expedite the convergence to quadratic level, that is the convergence will be quadratic, unlike gradient based techniques, which is where only linear convergence is possible. Here it is quadratic, just as in elasticity, right. So we will also discuss briefly in the next lecture how rate dependent plasticity can be interpreted as a mathematical regularization, okay, of the Moro-Yoshida type, but we will come to that as we go along. So thank you very much for listening in, and this will be all for the present lecture. I will see you around the next time. Thank you.